Hello everyone and welcome to this module on polar decomposition. So after polar decomposition, we will have a short introduction to the right and left Cauchy-Green tensor. You already get to know the right Cauchy tensor or C tensor if you recall. And then we have a discussion on the objective and non-objective tensors, which is somehow related to the right and left Cauchy tensor and some other tensors or different types of tensors like vectors and scalars. We're going to discuss to see what these two terms imply. All right, so let's get started by the polar decomposition. Decomposition theorem. In the previous module, if you remember, we introduced two type of spatial transformation. We said that we have d small x is equal to d to f dx, and this f we introduced r tensor, which was the rigid body motion, the local rigid body motion, and we also introduced the u, which was the stretching tensor or the pure stretch tensor. In polar decomposition theorem, we basically we can say that it can be proved that any transformation can be written in form of a combination of these local rigid body motion R and pre-stretching U. So basically the polar decomposition theorem says that F is equal to RU, or F is equal to VR. This is the polar decomposition theorem. And here U and V, or maybe I can write them separately. So this is the right stretch tensor. V is the left stretch tensor, simply because they sit on the right and the left side of the equation. And R is an orthogonal tensor, or the book said it's a proper orthogonal tensor. And you have to remember that what we already said in the previous module about U can be applied to V as well. So U and V, there are positive definite. So we have positive definite tensors in here, and symmetric positive definites. So we have symmetric positive definite. This also holds for V in here. And let me just give you the geometrical interpretation of this decomposition theorem. So here you can see we have F is equal to RU. So, sorry. So F is equal to RU. And we know that d small x is equal to f d capital X. You already remember this. This is the deformation gradient. So if we put this in here, so we get dx is equal to ru, ru dx. And here you see that we have u dx first. So here we have first stretching, and then we have the rotation. First we have to calculate this. So therefore we have here first stretching, and then we have rotation. So suppose you have a coordinate like this, and you have something like circle in here or a sphere or whatever. So if I plot a line from here to here, a vector from here to here, this is the initial or undeformed configuration. I have a point P in here at the center, and I have this point Q on the circumference of the sphere. I have this as dx. So first I have stretching. Therefore, in my basically in my deformed configuration, I first have kind of stretching, for example, like this. So I can point to the center of this ellipse with small x. So I have P in here, and then, for example, Q is here. Something like this. This is U dx. And then, so I can also change this, then rotation. So this is the rotation. And here I have this stretching first. So for the rotation, then I have the rotation. So then I have something like this. So then this is Q, for example, in the deform configuration. Then this is basically RU dx. This can be extrapolated to F equal to VR. Dx is F d capital X. Therefore, we have dx equal to, so first we have this V, and then we have this R dx. So first we have rotation, and then we have stretching. So if I plot this coordinate system again, I have my sphere in here. So I have my initial vector x in here, this is P, and this is Q, and this is d capital X. So first I have a rotation. So I get something like, I get something like, So here it is. I have small x in here. This is P. For example, it rotated like this. So this is Q, and this is R dx. So it is first rotated and then stretched. So I have Q in here, and this is V R dx. All right. So now we know what is the difference between RU and VR. Here we have first the stretching and then rotation. Here we have first rotation and then stretching. They're equivalent. All right. Next, we're going to establish some kind of relations in here. So, uh, how to relate correlation between U and V. So you can see in here that RU is equal to VR, right? So if I multiply both sides by R transpose, so I have R transpose, RU is equal to R transpose VR. Since this is an orthogonal tensor, so it becomes I. Therefore, I have U equal to R transpose VR. You can do the same in here. So you have RU is equal to VR. So here you maybe write it like this. So times each side with the R transpose, you have VR transpose is equal to RU R transpose. This becomes I, and then we have V is equal to RU R transpose. All right. Next, get to the introduction to the right C and left B Cauchy-Green tensors. So now we know the polar decomposition, which is a combination of stretching and local rigid body motion. So have you already had the right Cauchy-Green tensor? It was C, if you recall, and it was equal to F transpose F. And F, if you remember here, it was RU. So RU transpose RU, which is U transpose R transpose RU. This becomes R. So you have U transpose U. And you know that U is symmetric. So therefore U transpose is equal to U. You have U. And we establish here that C is equal to U squared. And remember here, the book actually used C is equivalent to this U2 because we have two tensors, they become multiplied to each other. Then we have the left Cauchy-Green tensor, which is defined as F transpose. So C is F transpose F, B is F transpose. So we have VR times VR transpose, which is equal to VR R transpose V transpose. Here becomes I. So we have V transpose. V is symmetric. So we have V, therefore P is equal to V squared. Or the book also said P is equivalent to V squared. All right. So now with this in mind, we have two new tensors in here. We have to derive all their, diagonals and off diagonals component and interpret them, which we will do in the next module. But before getting into that, I would like to show something, which is the usage of C and B tensor. So when we use B, when we use C, or which of these two tensors is actually more practical. Yes, we have to get to a topic of objective versus non objective quantities or tensors here, because we're dealing with tensors. And basically, this is the topic from part C of chapter 5 of the book. All right. So here I start with a motivation. Why do we need to have objective or non-objective tensors, and why we would like to use, for example, B tensor here, the left Cauchy-Green tensor, instead of C? In continuum mechanics, let's write it here in continuum mechanics, we would like to the position of observer should not change the quantity of interest. So that's why we are into this tensor B instead of C, because using tensor B, basically the position of observer does not affect the result when we use B. However, if we use tensor C, then the result is dependent on the observer. For this, you can suppose you're here, and here you have a Euclidean space where you have an origin and you have a right hand side unit basis. We call you observer. You're an observer, or that in continuum mechanics, the terminology is frame. And suppose your friend is here, for example, and He's basically on a bicycle like this. He has his own origin and E1, E2, and E3. He is also another observer or frame. And to differentiate this, we put star here to distinguish between your frame and your friend's frame. This is you, and this is your friend. So here I can write that also both coordinates in both frames rotate and translate with respect to each other. Suppose you have a point in here and a point in here, and the distance between these 2 points is ds, or let's say it's 1 meter, for example. So from your point of view, or from your frame, it is 1 meter, and from your friend's point of view, it is also 1 meter. It is also 1 meter if your friend starts cycling in a path, in an arbitrary path. It remains 1 meter. However, if you have a position vector here, x for example, you see this vector from one point of view, or your frame point of view, and your friend sees this from his point of view. Therefore, this vector x is dependent on your point of views, on your frame. Therefore, we call this this x frame dependent or non-objective, and this 1 meter or ds or whatever you call it is frame independent or objective. It's an objective quantity. All right, so we can write in here an objective quantity, or here we're dealing with tensors. Zero tensors are scalar, first order tensors are vectors, second order tensors and higher order tensors, is frame independent. And there is also one more thing that we have to take into account to call a quantity objective. I will just disregard it for the moment. So there is one more condition here. And I highlight it. Also, a non-objective quantity is frame. Remember, this is dependent. It depends on the observer. All right. So, for example, speed. If you, we may write these as examples, e.g., the distance And also we can say relative velocity or relative position. And here we can say, e.g., uh, position vector, this is a vector, also velocity vector, a scalar which is non-objective as speed. Yes. So for this one, to give you an idea, that a scalar field like distance could be independent, but also frame dependent. So it depends. So we can say that, okay, any scalar field is frame independent. Suppose you are here on an airplane like this. You're here, and this is also your friend in here. I don't know if you experienced this, but when you see yourself actually traveling at a speed of 900 kilometer per second, this is the same as this is the same for your friend who is traveling, who is flying at a distance at a velocity at a speed of 900 kilometer per second. But you can feel this is a very, very high speed, but you can't feel it. It's like you're not even feeling it. However, if you look at the window here uh, to the airplane of your friend, you will see that it is moving very, very fast. It is moving very, very fast. So this actually shows that your point of view, your frame, this is your this is you. Your frame is quite different from your friend frame. You, as an observer, experience a different speed than your friend, and this is mutual. Your friend also see you from his window that you are moving in a very, very high speed. Therefore, we can say that speed is a non-objective quantity. However, if you have a coordinate system like here, E1, E2, and E3, and your friend is here with a E1 star, E2 star, and E3 star, from his coordinate point of view and your coordinate point of view, your velocity is 900 kilometer per second, or his velocity is, I don't know, 980 kilometer per second. So this is not changing in different coordinate systems. This is only different from your frame or his frame. Therefore, we can say that if a quantity is different in frame, it does not mean that it is different in coordinate. Therefore, we have to put a line between frame and the coordinate. They're different. You can have transformations, coordinate transformations, in your frame, as many as you want. But a frame is different from coordinate. So let me just write this in here. So This is very, very important. So I may put it in a box. Change of frame is different from change of coordinate. Remember, you can perform any number of coordinate transformation within your frame. Therefore, we drew a line between frame and coordinate. All right. There's one more thing I would like to mention. Remember that maybe this one I also put it in a rectangle. Rigid body motion does not, body motion, it's better to write it should not, okay, so should not affect stress or strain tensor or mechanical properties of a material. So remember, if you're in your frame and your friend is in your frame, you have a bar under tension, for example, uniaxial tension. This is F, this is the stress is F divided by A. And this is the same from your frame and from your friend's frame. Also, if you have a Young's modulus of 200 gigapascal of that bar again, then from your friend's perspective or frame, it is 200 gigapascal, and it is also the same from your frame, which is 200 gigapascal. You don't see it as 200 gigapascal and your friend as 210 gigapascal. Remember this. So it does not change the mechanical properties of a material. So now let's get to this highlighted thing in here. What is this? There is one more thing. All right, let's answer this. I put a question mark in here. All right. Suppose an observer, think of an observer as a combination of a rigid body plus a clock. Therefore, if you are in your frame, you have X, your position, and T, and you want to transfer using a transformation to another frame. X star and T star, we show it by this. So if you recall from rigid body motion, we already mentioned that X is equal to CT plus RT times, it was capital X minus B. Here, if we call this CT the relative displacement, sorry, this is the relative relative displacement. And you can think of this as an orthogonal tensor, right? And we assume, since we assume a right hand basis vector, we can call this Qt. It's a proper orthogonal tensor. We call Qt proper orthogonal tensor. All right, so now I can write x star is equal to ct plus qt. I replaced rt with a proper orthogonal tensor, and I have x minus x0, an initial position. So if I have this position here, x1, and I have another position here, x2, and I want to measure the distance between x1 and x2, or the vector between x1 and x2, so I can put here x1, and then I have also x1 in here. So I have x2 star is equal to ct plus qt x2 minus x0. So if I subtract x2 minus from x1, I get this cancels out this one. Then I have qt times x2 minus x1. So if I rewrite this as b star and this as b, because you have two vectors in here, so you have b star equal to qtb. So simply from here, you can see that your another frame, suppose think of this as your friend frame, is equal to a transformation times your frame. So if you find this proper orthogonal transformation or tensor, you can transform your frame to your friend's frame. We can also do this for, let's say, for a tensor. And if you remember, this is one of the transformation laws we studied in module 1, where we had, for example, A was equal to Q transpose, A prime was equal to Q transpose A. It was this because we filled in the transformation, this Q matrix, vertically. But if you fill in this Q matrix horizontally, the elements, you get something like this. So this is the same as the transformation law we had in the first module. So let's do this for a tensor. Now, for a tensor like T. So we have your frame, C is equal to TB. So this B vector is basically transformed via this T tensor to C. And then we have C star is equal to T star, B star. And here, remember, C and B are objective vectors or quantities here. But since they are vectors, we put vectors in here. So we have C star equal to, if they are objective, maybe I can write it, this is the objective vector transformation. So it is Q C star, because we have C star equal to Q B, or maybe QT C, and B star is equal to Q T B. Perfect. So now if I start from here, C star is equal to T star, B star is equal to. So I have B star, sorry, if I start from here, QT C. So I have QT and then I have C. So I have QT, then I have T. B, C is this. So maybe if I call this one 1, this is 2. I don't know if I had 1 or 2 here. Nope. All right, so this is 1, 2. So from 1, write this, and then from 2, this is 2, and this is 3. So from 3, I write this. This is equal to, instead of B, I can write this as Q transpose T B star equal to Q transpose QB, which is I. So this becomes B. So I write this as 2. So from 2, I have Q transpose T B star. Therefore, I can write this C star is equal to Q T T Q transpose T B star, or I can write this simply as T star and B star, where this T is basically Q T T Q transpose T. So you can see here that again, similar to the objective vector, this is an objective tensor, you can see that if we had T prime, it was Q transpose TQ. It is similar to this equation in here. So we have this, let's say, transformation law for the tensors. So we can conclude that any tensor that follows the transformation law and is frame independent is an objective tensor. So the answer to this question is basically so if I paste this in here, the answer so it should follow transformation laws. The transformation laws for the tensors, of course, because here we are talking about tensors. So if I just copy this definition from here, and paste it here, and follows, maybe blue, follows transformation laws for tensors. All right. So now we can say what is an objective quantity. So if we can find an objective quantity, we had C and B. If we can find which one is objective, then due to this motivation here, we can say we can use it in continuum mechanics because it is independent of the frame or the observer. Great. So, before getting into whether C or B is objective or vice versa, let's do some examples in here. Let's get started by example. Example 5.561. Okay. So the first part of the example says that prove that dx is an objective vector. All right. So we have 2 points here. We have one here and one here, and we have dx. And we want to show that dx is an objective vector. So it is independent of the observer or frame. So if you remember, we had x dot equal to ct plus this orthogonal tensor times x minus x0. So this is basically x, and x star plus dx star, so this is up until here, this is dx, is equal to ct plus qt x plus dx minus x0. So if I have, this is 4 and this is 5. So if I subtract 4 from 5, then I get dx star is equal to, this cancels out this, so I have qt dx. Perfect. We get that a vector is following the transformation law. Therefore, dx is an objective vector. The next part of the example says that prove ds, which is the dimension of dx, is also an objective scalar or quantity here. Since we are dealing with tensors, I put a scalar here. All right. So we know that ds star squared is dx star dot dx star. We had this before. So dx is nothing but qt dx dot qt dx. But I can write this as dx q transpose t. So this is dx dot q transpose t q, qt dx. Since they're orthogonal tensors, this become I, and then we have dx dot dx, which is equal to ds squared. Therefore, ds star is equal to ds, and if you remember, alpha prime was equal to alpha. It was the transformation law for the scalars. Therefore, we can say that ds is an objective scalar. Okay, let's get to the next example, where we have example 5.562. So in the first part, it says that show the velocity can be found from in another in a different frame. It's better to say a different frame can be calculated from this expression here, qt dot x minus x0 plus c dot t. So if you recall from here, we had x star. So if you take the derivative of this with respect to time, sorry, dt of dx star is equal to, so this ct becomes c dot t, which is essentially dct with respect to dt. From dynamics, if you remember, we put this c dot t plus the derivative of this times this one, so it is q dot t x minus x0 plus this one times the derivative of this with respect to t plus qt dx dt, since x0 is only a scalar value. So here we have v star is equal to ct c dot plus qt x minus x0 plus qtv, which is the same as here, this q dot. All right. Next, it says that the velocity gradient in another frame is equal to qt del v q transpose t plus q dot q transpose. The gradient, if you remember, was v star of x plus dx, and of course these are in the star, minus v star x and t divided by dx star. So we use the same definition here. So we need v star x star plus dx star and t is equal to, so from here we have it. So there's also one more thing I want to mention here. So if you look at here, you see that only this part and this part, if we have these two parts, then we could say that the velocity is an objective vector. However, we see this extra part in here. This is the extra part. And this is the reason why the velocity is not an objective vector. So, therefore, velocity vector is non-objective. Okay, so from here I write c dot t plus q dot t, and then I have x plus dx minus x0 plus qt. I have v of x plus dx and t. Then v star x, star and t is equal to c dot t plus q dot t times v, or no, it is x plus x minus x0 plus q t. This is v of x and t. So then I have 6 and 7. So del star v star dx star from here is equal to 6 minus 7, which is, this cancels out with this. We have q dot t times x dx, only the x remains, plus here we have Vx plus dx and t minus v of x and t, and that's it. All right. And this is if we apply the same definition here, this is del v dx. All right, so I may shift this a bit down. So we have del star v star dx star is equal to q dot t times dx plus del v dx. And remember here, everything is based on dx. So I use dx star is equal to q t dx. And replace this dx star with this. So I have del star v star dx, oh sorry, q t dx is equal to q dot t dx plus del v dx. So if I move everything to the left hand side, so I have q and factor out dx, so I have qt minus q dot, sorry, is this q dot? Yes, q dot, let me check. Okay, so this is q dot, but this is q dx plus qt times this. So I have this dx plus, this is qt, and then I have here dx plus qt del v. So I have qt, so I have qt here, q dot minus qt del v whole times dx is equal to 0. Dx can't be 0, therefore del star v star qt minus q dot t minus q t del v is 0. So if I time this side with q dot, sorry, q transpose, so this become del star v star qt q transpose t, so this become I, so I have I in here minus q dot t q transpose t minus qt q transpose t del v, oh sorry, this qt del v qt transpose is equal to 0. So finally del star v star is equal to q dot t q transpose t plus qt del v q t t transpose is equal, oh sorry, is this. All right, so if you look at this expression here, and if you compare this with you know, with this one here, this transformation law here, qt q transpose qt q transpose, if you only had this part, we could say that, okay, del v, the velocity gradient, is an objective tensor. However, we have this extra part in here, therefore we can't say that it is an objective tensor. Therefore, velocity gradient is non-objective. All right. The next example, which gets us much closer to understand whether B or C is objective, um, is this example 556.3. So it says that if you have F star is equal to QTF. So it says that show that the deformation gradient in another frame, in a different frame, is the product of a tensor with this F in here. So you know that dx is basically f d capital X, and in dx star is also f star dx star. Also, dx star is itself qt dx in here. So from these two, we can conclude that dx star is equal to this. So we can write that f star dx star is equal to qt dx. And from here, substitute this, we get that f star dx star is equal to qt. Instead of x, I'm going to write f dx. And if you see here, we have dx star and dx. They are basically the same. They are the vector, the material vector in the reference configuration. Therefore, we can get f star is equal to qtf. Now we get to the last example where it helps us to get to our point, the last point in this video, that which one of B or C tensors are objective. Okay, so the first part says find the transformation law for the right Cauchy-Green tensor. So the Cauchy-Green tensor, the right was F transpose F, and in another configuration, in another frame, sorry, it is F star transpose F, where we know that F is, of course, F star is Q T F from this example here. All right, so now we can start from here. C star is equal to F star transpose F, which is equal to, so from this was, I guess, 6, 7, from 8. From 8, we have Q. I don't write T in here, so QF, sorry. It is QF transpose, and this is QF. This can be written as FQ transpose QF. This is nothing but the identity tensor, which is equal to F. Oh, sorry, this is F transpose. F transpose F. F transpose F is the same as C. So the transformation for C tensor is C. Therefore, it is not an objective tensor. This is also the same in here. Therefore, C is non-objective. For F, also, you couldn't get something like Q T Q transpose, and then F. You couldn't get this transformation. Therefore, F is also a non-objective deformation, is a non-objective tensor. So let's do this for the left Cauchy-Green tensor. Here we have B is equal to F transpose, if you recall. Then we have in another frame, it is F star transpose, and F is, it's good to write it here. So F star is equal to Q F. It's already here, 8. So I start from B star is equal to F star transpose, which is equal to, from 8 again, I have QF star, sorry, I have QF, then I have QF transpose, which is equal to QF, F transpose, Q. This is also another kind of tensor. We call it, for example, B. Sorry, this is B. FF transpose. This is equal to Q, B, Q. Transpose. This is also transpose in here. Therefore, B star is equal to Q, B, Q transpose. You can see that the left Cauchy-Green tensor follows the transformation rule. Therefore, B is objective. And that's the reason behind our statement here that we said that we use B as the proper transformation, as the proper tensor in our calculations in here, because we want quantities that are observer or frame independent, because in continuum mechanics the stress and strain tensor, or the mechanical properties, shouldn't change with respect to the observer, or rigid, or for example, by the effect of rigid body motion. They have to be the same.